Okay, so let's do chemostat equations, but this time with the Tessier growth equation. And I'll be covering cases where we'll be adding adding a biomass product to the inlet feed, and I'll be covering the case where the maintenance coefficient KD is not 0, but I'm going to start off with the most easy case first and then work my way through the questions. So let's say first that it's a pure inlet stream of only substrate, and let's also say that we can ignore the cell maintenance coefficient for now, and let's draw a rough sketch. So no x naught, but we'll have s naught, and we have s and x in the outlet. There's a reactor volume V, and the same flow rates going in and out, so it's that steady state. So let's see the Tessier equation. The growth equation is like this, and it's actually exponential, so I guess this one, maybe it's not so popular because it's non-linear. Let's see what we can do with it. Okay, there we go. So what we want to do is isolate for in terms of s. It's not difficult to do. Divide by that. See, 1 minus, so you can just do that, so you can get rid of that negative there. Take the ln of it. Ln is the natural log. It's like log base e. Ks is s. Okay, there we go. And we know from before that if x naught equals 0, then, and also KD equals 0, then gross specific rate is net specific rate is D. So what we can do is actually just replace this this gross specific growth rate with a D. Let's put S there. Yeah, so see how it's nice? It's only in terms of constants now. And also, if there's no endless stream, and if you just use stoichiometry, you'll see that this is true. And you can prove this by doing mass balances with each species, but also because the question is simple, we know that that's going to be true as well. So that's that, and you can actually just plug in S there. And yeah, not difficult at all. Though it looks difficult because it's non-linear, but you just have to remember your log laws. And yeah, it's not so bad. There we go. Okay, so let's do something a little bit more challenging. So what if x naught is not equal to 0, but KD is? And we showed before that instead of unit being D, it's actually going to be this. There we go. And since KD is 0, unit is just UG. And actually we can just substitute that into the S equation. So let's do it. Substitute that in. Okay, and that's simple. And then for this one, it's just stoichiometry. Remember, the difference is just the substrate being consumed multiplied by this yield coefficient, which is just the stoichiometric coefficient for this biological reaction, and plus it'll have what we started off with, x naught. Boom. So there you go. Now you can also shove this back into that, and you can also shove that into that. See, now because now that we have inlet feed, it gets complicated. These equations are implicit. See how x is an s and s is an x. So if you asked for some unknowns, you might have to solve the equation simultaneously. It's not a problem. You just have to work out the math. But these are the equations that should be good enough. And now let's consider the last case. If x naught is not equal to 0 and maintenance coefficient is not 0. So take the old equation and now we know that, well, UG equals, well, gross specific growth rate is the net specific growth rate plus the maintenance coefficient, and we just plug that into what we found before. Again, you want to work it all out by hand if you're doing it, but I'm skipping a lot of steps. See, now we have a KD term over there, and that's pretty much the only difference. And then x changes a lot. X actually has x in it as a function, so you don't really see what the equation looks like. You'll see. So the thing is, you're wondering, I got this question as well, like why is there no plus x naught? It's because I put, see how x is in here as well. We can solve in terms of x, but I think that this is enough. If you isolate that, yeah, you should be able to get something that looks a bit more familiar. See, because it's implicit right now, it's not explicit. X is a function of x. And yeah, these are the two equations you'll have. So basically, yeah, that's how you can model the equation under different kinds of chemostat conditions, and this time it's with the Tessier equation, which is non-linear, but it's not so bad, because you just have to work through the log steps carefully. And yeah, because a lot of people will just, on exams, they'll just make an arithmetic mistake somewhere around here, and then the whole thing ends up being messy. But if you work through it, you'll notice patterns. For example, you see 1 minus this kind of stuff. You see 1 minus a lot in these biological questions. We've seen it before. And yeah, just work your way through it. So I hope that this helped you out. If you're really confused about this, you probably just want to see the Monod version of this, the chemostat with the Monod equation. In that exercise, I show you how I go through all the steps in deriving the formulas. Here I'm skipping a few steps because I'm just using a new growth rate. But really, the growth rate is only when you plug in UG, which is usually done at the last step. So a lot of this has been derived already. So if you're feeling confused, check out the Monod equations. They'll help you out a lot. So I hope you enjoyed this video.